FMEA analysis, preventing failure before it happens. Failure modes and effects. Analysis, or FMEA, is a structured methodology designed to prevent failure before it occurs. In industries like aerospace, automotive, healthcare, and semiconductor manufacturing, a single failure can be catastrophic, resulting in high costs, regulatory breaches, or safety hazards. FMEA empowers teams to proactively identify weak points in a system, whether it's in the design of a product or the execution of a process. By systematically assessing potential failure modes and their effects, organizations can mitigate risks before products hit the market or processes are launched. This makes FMEA not just a quality tool, but a safety and reliability strategy. Throughout this course, we'll explore the step-by-step process of FMEA, discuss how it applies to both design and process stages, and highlight best practices. We'll also examine a real-world example from semiconductor equipment and explore tools that support FMEA implementation. Course overview. The course covers everything you need to build a foundational understanding of FMEA. We'll start by asking, what is FMEA? From there, we'll explore the two main types, Design FMEA, or DFMEA, and Process FMEA, or PFMEA. After understanding the core definitions, we'll walk through the FMEA step-by-step process, from assembling a cross-functional team to planning corrective actions. Then, we'll examine both the benefits and challenges that organizations commonly face when implementing FMEA. Next, we'll explore best practices that ensure FMEA is used as a living iterative tool. We'll also look at the FMEA scoring system known as RPN, which helps prioritize issues based on severity, likelihood, and detection. A real-world example will show how FMEA can be applied in semiconductor manufacturing. Finally, we'll introduce leading FMEA software tools and wrap up with key takeaways and an open Q&A. By the end, you'll understand why FMEA matters and how to apply it effectively. What is FMEA? FMEA stands for Failure Modes and Effects Analysis. It's a systematic and proactive method used to identify potential failure modes in a product or process before they happen. The goal is to assess what might go wrong, determine the effects of each failure, and understand their root causes. Then, the process assigns scores to quantify risk based on three factors: severity, occurrence, and detection. These scores combine to form the Risk Priority Number, or RPN. With this structured data, teams can prioritize actions and plan preventive or corrective steps. FMEA is not a reactive tool. It's applied proactively during design or before process launch. Design FMEA, or DFMEA, focuses on components and systems, while Process FMEA, or PFMEA, targets manufacturing steps or operations. By embedding FMEA early, companies reduce defects, improve quality, and ensure reliability. It's a cornerstone of quality engineering in high-stakes industries. Why FMEA matters? FMEA is critical because it directly improves reliability and quality. When failures are prevented early, products and processes become more dependable. This lowers risks tied to safety, cost overruns, and damage to brand reputation. In regulated industries, such as aerospace, automotive, and healthcare, FMEA is often a compliance requirement. Standards like ISO 9001, IATF 16949, AS 9100, and the FDA's Quality System Regulation specifically call for proactive risk assessments. Beyond compliance, FMEA also reduces warranty claims, rework, and scrap. It helps organizations focus their resources on the highest impact areas. Data shows clear impact. Defect rates and costs both decrease significantly after FMEA is implemented. In high-stakes industries, failure can mean more than inconvenience. It can threaten lives or cause irreparable damage. FMEA helps organizations move from a reactive stance to one of prevention, ensuring that customer satisfaction and safety are top priorities. Types of FMEA, DFMEA, and PFMEA. There are two main types of FMEA: Design FMEA, or DFMEA, and process FMEA, or PFMEA. DFMEA focuses on the design of products or components. It is typically performed early in the design phase, before prototypes are even built. Examples of design issues include circuit failures, material fatigue, structural weaknesses, or software algorithm flaws. By identifying these early, engineers can adjust the design to eliminate or reduce risk. PFMEA, in contrast, looks at the manufacturing or operational processes. It's usually applied before a process is launched or during process improvements. PFMEA helps identify issues like tool wear, operator error, process variation, or maintenance failures. Both types are essential. DFMEA uses design specs and CAD models, while PFMEA uses process flows and work instructions. Together, they provide full lifecycle coverage, ensuring risks are addressed from initial design all the way through to final production. The FMEA scoring system, RPN. At the core of FMEA is the Risk Priority Number, or RPN, which helps quantify and prioritize risks. The RPN is calculated as the product of three scores: severity, S, occurrence, O, and detection, D. Severity measures how serious the consequences are, from 1 meaning negligible to 10 indicating a dangerous, undetectable failure. Occurrence estimates how likely the failure is to happen, 1 for extremely rare and 10 for inevitable. Detection gauges our ability to catch the failure before it reaches the customer, where 1 means near certain detection and 10 means it likely won't be caught. The higher the RPN, the more urgent the need for action. Typically, an RPN above 100 is considered high risk and prioritized for mitigation. For example, if a circuit board failure scores 8 in severity, 4 in occurrence, and 6 in detection, the RPN is 192, definitely a red flag that requires intervention. FMEA Step-by-Step, Part 1. FMEA begins with a structured 5-step approach. Step 1 is assembling a cross-functional team. This group should include individuals from design, engineering, quality, operations, and technical support. Diverse perspectives help identify more risks. Step 2 is defining the scope. The team must clearly specify whether they're analyzing a product, component, subsystem, or process. Step 3 involves listing all functions and requirements. These describe what the product or process is expected to do, including performance targets. Step 4 is identifying potential failure modes. What could go wrong, like leakage, cracking, or misalignment. Step 5 describes the effects of those failures. This includes assessing how each failure impacts system functionality, safety, or customer experience. These steps lay the foundation for a detailed, data-driven risk analysis, making sure nothing is missed before moving to scoring and corrective actions. FMEA Process Flowchart, Part 1. The FMEA process begins with 5 foundational steps, structured into a repeatable flow. First, assemble a cross-functional team with expertise across the product or process lifecycle. This diversity ensures that failure modes aren't missed. Next, define the scope clearly. Know exactly what's being analyzed, whether a mechanical component, software module, or manufacturing step. Then, list all functions and requirements, which describe the intended operation and performance expectations. This baseline helps identify deviations. From there, identify potential failure modes, specific ways each function could break down. Lastly, describe the effects of those failures, focusing on how the system, user, or downstream process would be impacted. Each of these steps feeds into the next, creating a systematic workflow that ensures no critical failure is overlooked. FMEA Step-by-Step, Part 2. FMEA continues as an iterative cycle focused on continuous improvement. Step 6 identifies the causes of failure, such as poor design, material flaws, or human error. Understanding root causes helps target effective solutions. Step 7 assigns scores for severity, occurrence, and detection. Each failure mode is rated on a 1 to 10 scale using standardized criteria. In Step 8, these scores are multiplied to calculate the RPN. This quantifies risk and allows comparison across failure modes. Step 9 prioritizes corrective actions, focusing first on high RPN issues. Actions may involve design revisions, new controls, or process changes. Finally, Step 10 reevaluates the failure modes after improvements are implemented. Updated RPNs verify whether the risk has actually been reduced. This cycle, identifying, assessing, correcting, and rechecking, is what makes FMEA a powerful, living tool for long-term reliability and safety. Example: FMEA in semiconductor equipment. Let's look at an FMEA example from semiconductor manufacturing, specifically targeting a vacuum pump system in an atomic layer deposition, or ALD tool. The scope is to prevent vacuum pump failure, a critical system for process integrity. The action plan includes multiple steps. First, updating the preventive maintenance checklist to ensure routine tasks aren't missed. Second, replacing seals every 1,000 hours to reduce leak risk. Third, installing temperature sensors for real-time monitoring of pump performance. Finally, retraining technicians on proper oil handling and contamination prevention. These actions target common causes of failure, improve detection, and reduce severity. After implementing the actions, the RPNs for all identified failure modes dropped below 100, indicating acceptable risk levels. The maintenance workflow also became more proactive, incorporating steps like oil inspection, performance checks, and part replacement. This example shows how FMEA drives reliability, especially in precision tools like ALD systems. Benefits of FMEA. Organizations implement FMEA because it delivers concrete, measurable value across multiple dimensions. First and foremost, it reduces risk by identifying and mitigating failures before they happen. This improves overall safety and reliability. Second, FMEA leads to higher quality, whether it's in a product design or a manufacturing process. Third, it enhances cross-functional collaboration. Because FMEA involves input from design, quality, operations, and more, teams learn from one another and break down silos. Fourth, FMEA offers cost savings. By preventing defects early, companies reduce warranty claims, scrap, rework, and recalls. It also boosts audit readiness and compliance with standards. FMEA encourages teams to focus limited resources on the highest impact areas based on data, not guesswork. Most importantly, it fosters a culture of prevention rather than reaction. Instead of fixing problems after the fact, teams proactively design out risk and improve customer satisfaction from the start. Common challenges in FMEA. Despite its benefits, FMEA isn't always easy to implement effectively. One common challenge is dealing with too many failure modes, which can overwhelm teams and dilute focus. The solution? Prioritize failure modes based on RPN scores and their criticality to safety or performance. Another challenge is making FMEA a check-the-box activity rather than a living tool. To overcome this, FMEA must be embedded into the product development or process improvement workflow, not treated as an afterthought. Lack of training is also a barrier. Teams may not know how to score properly or interpret RPNs. That's why providing training and clear scoring guidelines is essential. Finally, some organizations struggle to update their FMEAs after corrective actions are taken. Continuous improvement means revisiting the FMEA regularly to verify if risks have been reduced. The real challenge isn't completing the form, it's using FMEA to drive lasting improvement. FMEA software tools. Specialized FMEA software tools can dramatically improve the efficiency and consistency of your analysis. These platforms allow multiple users to collaborate in real time and manage complex projects. For example, APIS IQ FMEA offers a comprehensive environment for managing FMEA data across projects. Reliasoft XFMEA brings advanced reliability analytics and is widely used in engineering organizations. Siemens Polarion is an enterprise-level application lifecycle management platform that supports FMEA integration with other systems. PTC Windchill Quality Solutions includes FMEA capabilities within a broader quality management framework. Intellect FMEA software provides a configurable QMS platform that organizations can adapt to their needs. These tools not only streamline data entry and analysis, but also help enforce process discipline. Choosing the right software can reduce manual errors, improve collaboration, and make FMEA an accessible, repeatable, and impactful practice throughout the organization. Key benefits of FMEA software. FMEA software brings several high-impact benefits that elevate traditional paper-based or spreadsheet-driven processes. One major advantage is real-time collaboration. Multiple users from different departments can contribute simultaneously, ensuring everyone's input is captured efficiently. Version control is another strength. Every change is logged, making it easy to trace revisions and maintain accountability. Standardization is built in, so teams across the company use the same templates, language, and scoring criteria, increasing consistency. Integration with other enterprise systems, such as Product Lifecycle Management, PLM, Enterprise Resource Planning, ERP, and Manufacturing Execution Systems, MES, ensures data flows seamlessly between platforms. Finally, many FMEA software tools offer powerful analytics, enabling users to visualize risk trends, monitor performance, and generate reports. These capabilities not only improve efficiency and traceability, but they also drive smarter decision-making and accelerate your continuous improvement efforts. Best practices for FMEA implementation. To maximize the value of FMEA, organizations should follow a set of best practices. Begin with a strong cross-functional team, drawing expertise from design, engineering, quality, operations, and even customer experience. Each perspective adds unique insights into potential risks. Standardize your scoring system to ensure consistent severity, occurrence, and detection ratings across teams and projects. Clear documentation is essential. Every failure mode, cause, and control should be explicitly recorded. Schedule regular reviews of your FMEA to capture new insights, process changes, or lessons learned from the field. Prioritize items with the highest RPNs, especially those tied to safety or mission-critical functions. Most importantly, embed FMEA into your development workflows so it becomes part of your team's DNA. Treat FMEA as a continuous process, not a one-time event. Start with pilot projects, train your team, and track risk reductions to celebrate success and build momentum. Summary and key takeaways. FMEA is a powerful, proactive methodology designed to identify and prevent failures before they happen. It reduces costs, enhances safety, and boosts quality in industries where failure can have significant consequences, like aerospace, automotive, healthcare, and semiconductor manufacturing. FMEA provides a structured and repeatable approach to risk analysis, making it easier to uncover failure modes, assess their impact, and implement corrective actions. It's essential in both design and process phases through DFMEA and PFMEA. When applied correctly, FMEA strengthens customer trust, ensures compliance, and fosters a culture of reliability. Remember, FMEA isn't about panic during uncertainty. It's about preparation. Teams that embed FMEA into their daily practices are better equipped to handle change, minimize risk, and continuously improve. As you move forward, think of FMEA as not just a tool, but a mindset that anticipates problems and designs them out before they reach the customer. Questions and answers. Thank you for engaging with this session on FMEA. Now is your chance to ask questions, seek clarification, or explore how these concepts might apply to your specific area. Whether it's aerospace design, semiconductor processing, healthcare technology, or automotive systems. No question is too small, and your curiosity helps deepen understanding. If you're wondering how to structure a real-world FMEA, how to prioritize multiple failure modes, or which software tool might fit your organization best, let's discuss. You can also reach out after this presentation for further support. Remember, implementing FMEA well is a team effort, and your role in that effort is critical. Let's take a few minutes to address any final questions or topics for discussion.